spectroscopy is to study the structure of materials. So we use this technique in the other way, but it's very useful. So this outline of my talk, the first is for the overview. It's a very simple background to show like why we are using Raman spectroscopy for temperature measurement, and what's the advantage, like the unique things for this technology. It must be something unique, otherwise, we won't choose. So then I will go through a few of the research areas we are doing the particle-induced near field for the temperature measurement using Raman spectroscopy. The other one is for near field on the AFM tip. That's the tip-enhanced Raman, but we focus on the temperature measurement. The third one is for the interface energy coupling. This is one of the main research directions we are doing still right now every day using Raman spectroscopy. The last one is for the time domain differential Raman, because right now for the Raman spectroscopy, people use a laser, it's a CW laser. It's like the laser is irradiating the surface all the time. So we change the way how the laser is like irradiate the surface to study some like a transient phenomena. So this slide shows some traditionally like how people measure the temperature. You see the one on the top left. This one is like the thermometer, the very old time people use, but still it works really good. And this one is a modern one. It's good. It's also very fast. So this one people use for the year temperature measurement is by measuring the infrared radiation. So this one is we call it temperature gun or thermal gun. Is measuring the radiation. So the last one on the bottom is the thermocouple. So if you have a temperature rise, so you measure the voltage difference between these two leads. So that's the normal ways. The limit like this, for example, if you want to use like some summist or thermocouple, you measure the temperature. So the resolution is really limited. Even, for example, if you use thermocouple, I think you can go to maybe 50 micron. That's the smallest one you can go. You cannot go smaller. It's really difficult. And every time you try to attach the thermocouple to the surface you want to measure, you introduce like interruption. So you are not measuring the real temperature. You give some interference. So this one shows the optically why we are doing the Raman and what's the background. So probably a lot of people have the experience. I mean, I have that one. Like when I was a kid, I use this kind of lens, focus sunshine, try to catch an ant, on the side. So for this kind of, if you use this kind of lens, the size you can focus, is kind of millimeter. And if you use like the micro spectroscopy, the optical one, the diffraction limit probably give you 0.5, 0.6 micron, the focus. That's the limit you can do. It's really difficult to go below that level. So this picture, this one shows if we place a particle, it's some micro size particle. So you can do the near field focus. And the light is focused really small area. I think the focus is like around 200 nanometer. Basically, it's less than that. So now the question like this: why people want to focus the light to this small size? Basically, you can do nano manufacturing. So you can use this tiny, tightly focused light. You can make lines on the surface, and you can make holes on the surface. So it's nano manufacturing on the surface. It's very useful. So, but the idea is like people know that if you focus the light, so you can heat up the material, it can melt. But nobody knows how high the temperature goes, because this area is really difficult to measure for the temperature. You cannot put a sensor here. If your particle on the top, it's really difficult to reach this area. So the first area, the direction I will show is like how we can measure the temperature in this tightly focused region. So this one gives some background for the Raman spectroscopy. I think you guys know a lot, probably more than I do. But this one shows, the Raman spectroscopy scattering. You have the Stokes scattering, anti-Stokes scattering. The interesting thing is the Raman peak. You see this one. The Raman peak basically is affected by temperature. So I think 3 ways the Raman peak is affected. When the temperature goes up, the intensity of the Raman peak goes down. Also, the Raman peak will be softened, will go to the left side, softened. And also, the line width of the Raman peak will be broadened. So you can check either way, intensity, the line width, and the Raman shift. 3 things, either one can give you the temperature of the local position. It's temperature sensitive, but the story behind is really complicated. It's like this. So this one I show some why it's complicated. For example, I said the temperature can affect intensity, Raman shift, line width. But the stress, if you have material, if you have local stress, the stress can affect the Raman shift a lot. So stress has very weak effect on the Raman line width and the Raman intensity. The other one, I think people didn't pay so much attention, but it's very critical. It's the out of focus effect. So in the past, we found if the surface we want to look at, if out of focal plane, very little. If you ask me like how little, like maybe half micron. So your Raman intensity, Raman shift, and the Raman line width, all of them will change. So that means the optical focus had another very strong effect on these 3. So that means in the experiment, we need to control the 3 things. And if they're kind of all of them exist, we need to decouple the effect to find the temperature, the one we want. Unfortunately, the good thing is it's doable. So, so this one shows, like if you have particle, our near field simulation by solving the electromagnetic wave, how the light is focused. So you see this scale bar is 200 nanometer. So it's really tiny. So this slide shows the particles. We use different size particles. So this one shows the particles. The biggest one we use is around 1.2 micron. So the company told us is 1.2 micron. The real size, this kind of varies between 1 point something until 1.2. But it's okay. We can measure the size precisely, then use them. So that's the particles we used. Is a silicon dioxide. We put the particle on the silicon wafers. And what we do, we scan the sample at the Raman laser. So like from left to right, we want to see how the Raman intensity, the Raman shift, and the line width, how they change when we shift this sample in space. So this one shows some picture, because the first time when we obtain this result, we are really excited. That time we thought the particle size, the laser we use, the focus is like 20 objective lengths, basically a few micron. It's it's not small, but it's very interesting. You can see that. You can see the Raman intensity changes periodically and smoothly. Completely gives the the surface profile of the particle. And also very interesting, the peak-to-peak location is exactly the size of the particle we use in the experiment. So then we check the Raman shift, gives another periodical variation in space. Also the line width gives another one. So all this kind of change, the intensity, Raman shift, line width, is induced by 3 things: stress, local temperature, and the optical focus because if your light is just below the laser, if your focus in the middle. So if your particle is on this side, the focus point is like a little off the center. So you have some focus defect. So first, you can see this one. Using the Raman, you can tell the particle size precisely. That's very interesting. The second one, so I won't go through some detail like how we decouple the effect. We call it deconjugation, or the stress, optical effect, also the thermal effects. So finally, we can determine, you see this one, highlighted one, the temperature of the silicon here. It's a very tiny spot. We can determine the temperature. So if I go back a little bit to show, basically we use the same light. The laser is focused here, so it's hitting the local area. But at the same time, your laser is exciting Raman signal from this location. So the signal goes back to the Raman spectrometer. So that means you are measuring exactly the location of the heating. The temperature is that location. So it's very interesting. And also, we can determine the stress in the silicon surface. I think it's the first time people can do this kind of temperature stress measurement in a tiny region. It's like 200 nanometer, tiny region. Probably Raman is one of the very few techniques can do that. Otherwise, it's so difficult. So we use many particles, and we ask ourselves if we can tell the size of the particle using the Raman spectroscopy, the scanning, what's the limit? And we tried 800 nanometer particles. We tried 400 nanometer particles. All of them were good. And the smallest one we can try, the company cell is 160 nanometer. And we scanned. You can see the intensity. Still, it tells you the particle size is 160. So basically, you can really, using the Raman spectroscopy, you can really go beyond this diffraction limit to study some surface feature size. It's a very tiny one. It's not only for temperature. You can study the surface feature size. So a lot of people basically ask us and like this, and you did a measurement, and how do you know your measurement is right? And no one has done that before. How do you know you're right? So the only way we can check out the result is we use simulation. First, we simulate the optical focusing effect. So we get the idea how much light is focused. Then we use this light as a heating source. We do another kind of simulation. It's like heat transfer to see the local temperature rise in the middle. And then we can compare the temperature rise with our experiment. So I will show you later for the single particle. The agreement is really exciting, really good. So the few slides I showed is for like particle array. You have many particles. And then we push the limit. We pick one single particle using the Raman spectroscopy to do the scanning. So this is my single particle. And the size is 1.2 micron. So we scan from left to right. I mean, if you look at the picture, you probably think everything is good, but the real experiment takes time. So we need to identify the particle, then bring the particle to the middle of the light, then do the scanning. So, the story like this: if your particle is not directly under the laser, so the focusing is here. Direct on laser, the focus is here. So to the other side, your focus is here. So basically, if you change the particle position, you are changing the location. You are detecting the Raman signal. So this one, the first one shows how the Raman intensity changes with the location. You can see it's like this one is a peak location when the particle is directly under the laser beam. And for the omega and the line width, they have something shift. So for the shift, later we find it's like this. It's like in the experiment, the laser, the center of the laser basically is not exactly the center of the optical path. So they give this kind of shift. Otherwise, it should be in the middle, the same location. So basically like this. If you do the scanning, this one can be used to tell how good the laser focusing is. Is the laser center exactly in the middle of the optical path or not? And also use this one, we get the temperature rise of the silicon and the particle, also the stress. So we did the simulation. So this time we simulate the optical field, then use the optical field as the heating source, solve the temperature field. And then use the temperature field to solve the stress field, because whenever you have a local temperature distribution, if the temperature distribution is not uniform, so you will have like stress. And you see, the simulation gives a temperature rise 51 Kelvin, and our experiment measurement is 58.5. It's really close. I mean, it cannot be identical. If identical, I mean it's wrong. So because why simulation, why is the experiment? They are totally different using different ways. So for the stress, we see some difference. The simulation, we show a stress like 30 megapascal. The experiment measurement gives like 160 megapascal. So this kind of difference is expectable. It's like this. In the simulation, we assume the light is coming in parallel. It's like by the experiment, the light is focused, has an angle, so the numerical aperture. So it's different. So that means in the experiment, the focusing is stronger. Means the temperature distribution in the space is like the gradient is higher, so the stress should be higher. So that's for the particle. And after we finish that work, we try to extend the technique. We check the focusing and glass fiber. This one is like a 6 micron glass fiber. So you can see the laser intensity distribution. So, sorry, the Raman spectroscopy, the Raman signal. So gives exactly the diameter of the glass fiber. Is very interesting. Otherwise, you know, if we want to measure that glass fiber's diameter, we have to go to SEM. So now using the scanning Raman, we can tell the size precisely. And also that's the omega and the line width. This kind of variation in space is kind of complicated because if you have multi-scattering of the light, you have to track the light rays, how they are kind of reflected. So, but all of them can tell you the size of the glass fiber. And same way we did before, we can determine the temperature rise of the silicon and the glass fiber because of the heating. So that's the heating. That's the stress. So this kind of near field focus, you can use a particle, you can use a glass fiber like a micron size, you can go to sub-micron size. It's okay. So another kind of near field focus is called TP enhanced Raman. I think people know a lot of things about this. Probably the B&W Tek technicians, I think they know a lot. For the TP enhanced Raman, people focus the light to AFM tip. So the light basically can be focused very tightly on the tip. So if you ask me like how tight the focus is, this region is only like a few nanometers, very tiny. So that means you can detect the Raman signal within a region like a few nanometers. And I mean, this temperature here is so difficult to measure, almost impossible. The only way to do is like we can measure the Raman signal from this location to get the temperature. So other ways, I didn't find that other ways people can measure the temperature here. So this one shows like how small the focusing is, and it's based on our simulation. You can see this one is like a 30 nanometer scale bar, and you see the focus is very tiny. It's very tiny, like some 10 nanometer. So very tiny size. For this research, we have done like two things. First, we check the temperature rise of the tip, the AFM tip, because if your light coming in, your light is also irradiating the surface of the tip. So the tip is also has some heating, and we first started the heating effect of the tip, and the tip is very tiny. You see the tip size. This one is an AFM tip. Is like a 5 micron. The total length of the tip is only 18 micron. It's very tiny. So, but we managed to measure the temperature rise of the tip using Raman spectroscopy if the laser is hitting the tip. So this one shows the schematic of the experimental setup, how we focus the light to the tip, and we have a nano stage, so we shift the tip in the X, Y, or Z directions. So first we show like three very typical comparison. One is in the tip middle. So the other one is on the tip base. The other one is on the bulk silicon. So bulk silicon, if you use a laser to shoot, measure the Raman spectrum, this one has very low temperature because the silicon piece is huge. So has very high thermal conductivity. You can see this one. That's from the silicon. And for the AFM tip, the base is also silicon piece, but the base is huge, but it's not as big as a bulk silicon. So you can see this one here. Means it has temperature rise. You see, shift to the left side. Also, it's broadened line width. And this one, we shoot in the middle of the tip. So that means your area is getting smaller. So the energy of the laser is not easy to be like a conductor. So the temperature rise higher means the peak is broad and is very shift to the left more. So this is a very, I think, representative one to show even same material is like silicon, but each of them has different temperature rise. You can see the Raman spectrum really change a lot. So what first one is we shift the peak, the tip from the bottom to the top to check the temperature rise of the tip. So you can see the temperature rise. So when the tip is in the middle here, the temperature rise is highest one. It's like 756 Kelvin. So this one shows if we move the laser along the tip, like from the peak to the base, how the temperature rise changes, like this. We tried two different laser energies. The third one is in the middle of the tip, and we change the laser energy from low level to high level, how the temperature goes up. So this one shows the same location. Nothing changed. The only thing we changed is the laser energy. So you can see for low laser energy, the green one, the peak is here. So if you make the energy higher, the temperature will go higher. So that's the second peak. And if you go the higher energy, the peak is here. Higher, so the peak is here. So this one clearly shows like the idea. If the temperature is higher, so the Raman peak goes to the left. One thing I didn't mention is like in the experiment, we have to do calibration, to calibrate how the Raman spectrum changes against temperature. So after the measurement, again, it's like we have to make the loop closed. So we do the measurement, and we show we try to do the simulation because no other people did that. We did a simulation to compare our result with the experiment. So in the beginning, for the tip enhanced Raman technique, I said, so the the AFM tip can be heating up. Also, the substrate can be heating up because the laser has a focus here. So the next one is we measure the temperature of the substrate and the laser heating. Just 1 second. So this is the technique, and so this one we use the free space Raman from B&W Tek. That's the first Raman we bought, and so we use the AFM tip. So the Raman spectrometer shoot the light to the tip end, also collect the signal from the tip end, and for the tip we want to make sure the tip does not give any Raman signal. So we use the tip and the cantilever is like gold coated, means it does not give any Raman signal. The signal is only from the substrate, is a silicon substrate. So that's the setup of the experiment. And because the laser is polarized, so we try to change the polarization to see how the polarization can change the heating. So this one shows like this. The black one is when the light is like 75 polarized to the tip, means they are almost like a normal to each other. Under this kind of situation, the absorption is really weak. So the Raman peak is on the right side. So the green one is like a 15 polarization, means the light coming in almost parallel to the AFM tip. So they can introduce a very strong eddy current in the gold coating. So the heating effect very strong, and you can see the peak moves the left side. So we measure the temperature from this one, from the peak, and the AFM tip is for the substrate. So because it's the first time we are measuring this temperature, basically it's the first time people can measure the temperature and the near field AFM tip is very challenging. So we try to make sure our result is good, is reliable. So this one shows if we shift the light, a little bit, so then the temperature rise goes down quickly. So that means the heating effect goes down very fast. So we want to make sure it's true. Otherwise, because no one knows what's the story behind. And then we simulate the optical focusing effect. Is a quite complicated system. A silicon substrate, we have silicon tip, the core, and we have the gold surrounding the tip. So we simulate the optical field focusing within this region. It's very tiny. It's like a sub 10 nanometer. And so finally, we calculated the temperature rise of the substrate as 235 degrees Celsius. And if you see the temperature rise we did in the measurement, you see, it's like 220, 225. It's already very close. It shows excellent agreement between the experiment and the simulation. So this work is basically conducted by two students. One is doing the experiment, the other one doing the simulation. So they are completely, separate from each other. We want to make sure it's kind of blinded, then compare the result. The final one is, I think, for the near field focusing, shows the unique things of the Raman spectroscopy. It's like non-contact. You can really measure some areas, for the temperature. It's almost like not measurable before. I think the most exciting one for the Raman spectroscopy for temperature measurement is the highest temperature resolution in space. Why is that? So this one shows the for interface energy coupling. This one gives the idea why the Raman spectroscopy is the most advanced one, most useful one. So this one we use the confocal Raman from B&W Tek. So after that time, I think the company discontinued the product. Still, I have a lot of friends. They are really interested in buying the confocal Raman. It's a great one. So This one shows, like for example, a lot of people talk about graphene, and graphene has very high thermal conductivity. So a lot of times they put graphene on substrate. So in the devices, the graphene usually they have heating. So the heat dissipation from the graphene basically is controlled by the interface resistance between the graphene and the substrate. So this one is very, very critical, very critical. Even graphene has very high in-plane thermal conductivity. That one is not important because graphene is very thin, so heat is not easy to go away along the plane. It's kind of like by the interface. So many people, it's a big area. People are doing research. They try to characterize the interface thermal resistance between graphene, even other 2D materials on the substrate. So, so this one shows the graphene on the substrate. I mean, even you can imagine, people can imagine graphene could be very flat. In a real situation, it's not. It's like a soft cloth on the surface. It's not like flat. So that means it could have a quite high thermal interface resistance between the graphene and the substrate. So the challenge is like this: how people can measure this interface resistance is very, very difficult. So because graphene is very thin, and you need to know how much energy you apply, what's the temperature difference between graphene and the substrate. So, so this one shows one of the experiments we have conducted is a graphene on silicon. So with the confocal Raman to shoot the surface. So interesting like this. One time you receive two Raman spectra. One is from the graphene, the single layer graphene. The other one, because graphene is very thin, transparent, you have signal from the silicon. So Dan, you can hear me good?
Yep, you're good.
Okay, good. So that means each time you receive two Raman spectra, that's a very, very unique thing. So that means from the two Raman spectra, I can determine the temperature of the graphene on the substrate. That's never been possible before. It's like a fingerprint, If you have you and another friend, it does not matter how close you two are. Your fingerprint is very unique. It's very unique. So from the fingerprint, I can, detect it's you or your friend. So this like even the graphene and the substrate, they are kind of nanometer separation, even atomic level. It's okay. Each one has its own Raman spectrum. That means I can tell the temperature difference between the graphene and the silicon. Then from the temperature difference, I can calculate the interface resistance. So that time when we came out with the idea, so we got some support from the Army Research Office, also from the National Science Foundation. So so this one shows the result. That's the graphene's temperature, and that's the silicon substrate temperature. So you can see they have difference. So this is the different energy absorbed by the graphene. So this temperature difference is determined by the interface resistance. So you can determine the interface resistance. It's a very unique one. And the other unique thing, because I mean, if you do the measurement, you measure the interface resistance, you can tell people, oh, my resistance is very small, means my interface energy coupling is very good. The two materials are very tightly contacted. Yes, but at the same time, using the Raman spectroscopy, you can optically, you can tell people how good the surface contact is. For example, if your silicon, that's a graphene. If the graphene is kind of curved, so that means every time you have the energy coming in, you have multi-reflection before the light is absorbed by the substrate. So that means you have interference at the interface. So whenever you have this kind of interference, the Raman signal is enhanced a lot, really a lot. It's like maybe 20%, 50%, or even higher. So that means you can use the Raman signal to tell people how tightly the interface is, between the two materials connected. So when we did the experiment, or also we use the Raman signal to tell people, is it good or not for the interface between the two materials? So this one shows after we did the measurement, we used the AFM to scan the surface. So you see this one on the right is a bare silicon. So it's very smooth. I mean, you can see the smoothness. It's like positive minus 0.25 nanometer atomic level. For the graphene, even the graphene looks smooth at the microscope, but it's not. A lot of corrugation. So means you should have, quite big interface resistance between the graphene and the silicon substrate. So for the interface energy coupling, we have done a lot of measurements. I here only show the one between graphene and the silicon. Also, we did between graphene and the silicon carbide, between graphene and glass. Right now, we are doing measurement between black phosphorus and silicon, molybdenum disulfide and silicon. So we are doing a lot of things using the Raman spectroscopy. The final topic I will cover is for the time domain Raman. Right now, even when we get the Raman spectroscopy from B&W Tek, the laser is CW laser. So that means you measure the temperature rise, you measure the heating effect. It's a steady state effect because everything is W. So later on, we did some work. Basically, we disassemble the spectroscopy, and we make some holes, and we introduce a second laser to the system. It's kind of very time-consuming, but we did it, and we use another laser. So this laser, we can do the modulation. You see this green one? That's the laser. So we can control like how long time the duty for the laser on and how long time for the off. So you can imagine every time when the laser is coming in, you have a heating. But the heating is very short. The material does not reach the steady state. So the Raman spectrum, you do the measurement, gives you average temperature of this very short heating time. So next, I make the heating time longer. I do the Raman measurement again. I get another average temperature. Then I try another case, a longer laser heating. I measure the average temperature. So I keep changing the heating time of the laser from short to long, and I measure the local temperature rise. Then this local temperature rise basically is determined by the thermal diffusivity of the material. It's another very important property. So we can measure that thermal diffusivity. The sample we used is a silicon cantilever. It's a very thin one. We measure the top end. And so this one shows, you see, if we change the heating time to very short one until very long, how the Raman shift changes and how the intensity changes. So all of them is related to the local temperature rise because nothing changed, only the heating time. Finally, we can determine the temperature rise. So this one is a time domain. The other two I can briefly introduce. The other one also we do the frequency Raman. And the laser beam is modulated from very low frequency, for example, from 20 Hertz until 1 megahertz. We get a laser from a company. It's a single longitudinal mode. So we can measure the frequency Raman. And very interesting. So that one also can measure the thermal diffusivity of the system. So that one already published. The other one we are doing right now is we combine a picosecond and a CW. So we use picosecond to do the Raman. So that one gives a very unique thermal response of the system. The CW gives another one. So we combine the two techniques. We can determine a lot of properties, even the electron diffusion people can never do before using the optical method. So my point is like this, even traditionally Raman spectrometer is for structure analysis, but it can be really used for other things, temperature, optical field, the feature size of the structure, and even for the electron diffusion. So finally, it's a summary, like the one I showed here. It's like Raman spectroscopy. You can do the sub-wavelengths, temperature, even the stress measurement, and also we can do the far field nanoscale imaging. I mean, far field is like using the confocal Raman. Everything is very large, but we can look at the temperature effect at like sub-10 nanometer, very small. Also, we can use the Raman-based probing to measure the interface energy coupling, like a mechanical stress, like also temperature, and also the local, even the spacing between the 2D material and the substrate is a very unique thing. And the final one, number 6, is for the time domain control. So you can do the time differential Raman, frequency controlled, also ultra fast Raman using picosecond. So we basically got to this area from 2009. I mean, 80 years has passed. So the work was supported by a lot of agencies, like the National Science Foundation, the Air Force, also the DOE, and Office of Naval Research on DARPA. Helps a lot. It's like basically each time, yes, you can see the structure, but also you can see a lot of things far beyond the structure. It's a very useful technique. I think that's for my talk. Thank you guys very much.
All right, so do we have any questions? Any questions at all? Yes.
Do these techniques work for other materials, or what other materials do they apply to? So, like, say, cell membranes or polymers. Would it work in this context?
Okay, so the question was, does this technique work for any other materials? Cell membranes, polymers, anything else?
Oh, yes, absolutely. One thing I didn't show, we are doing a research using for polymer, like the polyethylene and PMMA, and also PET, other materials. It works really good. The signal is really strong. And also, we have used this technique on like other samples, like organic, like human hair, some things. It's really good.
Thank you.
Yes.
Have you tried measuring the temperature, looking at the ratio of the Stokes versus the anti-Stokes intensities?
Okay, the question was, have you tried measuring the temperature using and looking at the difference between Stokes and anti-Stokes?
Very good question. Right now, the Raman spectrometer we have can only measure not only the Stokes, the spectrum, but you can. Anti-Stokes is also used. But one thing like this, for anti-Stokes, the Raman signal usually is much weaker than the Stokes Raman signal. So that's the reason we didn't choose. Second one is a lot of people, they use the anti-Stokes and Stokes, the ratio, the intensity ratio. You can use that one for temperature measurement. One thing is the measurement is like this. For example, if you want to do the temperature measurement, you want to make the integration time as short as possible. Why is that? Because if the time is very long, the stage, because even is the high level stage, the stage will have some tiny shift. So that one will give you extra like a focusing effect. So we want to make sure the integration time is very short, usually like 1 second or even 0.some second. If we cannot do that, we will set the stage, let the stage settle for 2 hours, then do the measurement. So to completely eliminate the focusing effect.
Any other questions? All right. In that case, thank you, Dr. Wang. I'll let you get offline now, and we will continue on.
Good. Thank you guys very much.
All right.